So SNIA believes in both open standards as well as open source, and we complement those by having a technical work group in the SNIA be allowed to have both items in their charter, right? They can have what we call a SNIA architecture, which is a standard. We usually take those on to ISO or JTC1. But we also have projects out there in GitHub that are open source as well. Typically, those open source projects are going to implement some aspect of the standards, such as a reference implementation or perhaps test clients as well. And so we do feel that both open standards and open source are very complementary and do need to be worked together. Our current project in open source is the CDMI reference implementation. CDMI stands for the Cloud Data Management Interface, which has been an ISO standard now since 2012. We just published a new version of that, so that'll be a 2016 version of the ISO standard. And our CDMI reference implementation has an open source repository on GitHub that anybody can access. And also now, because of our contributors license agreement project, they can also contribute to the CDMI reference implementation as well. And because of its importance of standards development as well, that means the adoption is not just a matter of picking up code and using it everywhere, but also allows independent implementations of the standards outside of the open source. Companies can develop proprietary information, proprietary code, as well as the open source adoption as well. Basic bottom line is that customers get what they need. They need the freedom to choose from multiple best-of-breed implementations. So Terry Hulett, Vice President, Systems Engineering and System Solutions Group, Everspin, is a VP of System Solutions at Everspin Technologies, where expands Everspin's capabilities and business strategy as a world-class solution provider.
Thank you, Rick. Mark, sorry.
So
thank you, Mark.
This is to the right to go down.
Okay. Hi, good morning. It's not that early, so it should be okay. At least I made it, so a lot of you did. I appreciate that. So as Mark said, my name's Terry Hulett. I run a group at Everspin by the name of System Solutions, and most of you probably know something about Everspin at this point. We're the MRAM guys, and we've been delivering MRAM to the marketplace for a long time, and you don't want me to sit here and tell you a bunch about MRAM. But I can't help pointing out a couple simple facts, right? We think of memory, okay, and that's got write characteristics, and DRAM and SRAM have been our constant model for memory for a long time. And the write characteristics are such that you can write it very quickly, and you can write it many, essentially infinite times. The CMOS wears out first. So we have things we consider storage, and I think NAND is going to be the lowest cost per bit for the next 10 years. So it's a solid-state storage device. But its write characteristics are the other end of the spectrum from things we think of as memory. Well, there's an MRAM technology that we have that actually falls in the category of memory and from its capabilities. It's got the endurance and the write performance that's close to, but not quite equivalent to the DRAM and SRAM technologies, but it looks like memory. The other things we call storage class memories are very, very good read buffers. They have a good cost per bit. It's not quite NAND yet, but hopefully they'll get there someday. And their read characteristics are much better than NAND. However, their write characteristics are only a little bit better than NAND, which means that the MRAM technology that we have is useful, even though its density is much slower than the other technologies. It really comes into play as a write buffer for things going to lower cost per bit storage. So that's the basic positioning of MRAM technology, and I'm going to move on because this is not about a chip technology session. Too many builds. So what we did was we actually took the MRAM technology and we made some SSDs out of it. The storage is all MRAM, and the capacity is tiny. And we were talking about megabit and gigabit chips today, so we have gigabyte type storage devices, but the performance characteristics are crazy. We're actually seeing less than 6 microseconds for 4K random writes from a standard NVMe driver. You use SPDK, we're down to below 3 microseconds for 512 byte writes. So its performance characteristics are radically different than things you normally think of as an SSD. When you add those characteristics into an SSD, now you can actually make SSDs out of lower cost per bit technology that fundamentally will give much better performance characteristics. But I want to show you a couple things that we've done with this device so we can really start to think about where persistent memory plays in the storage fabric. Okay? So if it hadn't been called the Fire Memory Summit, then there would have been a presentation where we were doing, we were actually showing how MRAM technology on a PCI card, and so it's an NVMe device that also has a memory mapped I/O capability. So it's byte mode addressable as well as block mode addressable. And so we were actually doing 64-byte messages from a client machine through a 40 gigabit per second network into memory on our card on the other machine. So there's actually the data is not going into system memory. It was actually going reads and writes into memory on the NV Nitro card. And that demo was going to be doing 2 microseconds to persistent memory on a remote device and 10 million messages per second. So now you can start thinking about, I can do remote logging. I can do remote messages, into persistence and, extremely low latency times. From a bandwidth perspective, it was still pretty good too. This demo was limited by the 40 gigabit network that we had to connect the two together. So what we decided to do next was, well, let's upgrade to a 100 gigabit network and upgrade to a later card from our friends at Mellanox. And it's, and so we're actually doing NVMe over fabrics to our device now. And out there, it's running at 19 microseconds for remote persistent storage at about 1.4 million 4K messages per second. And it'll sit there and do it all day long. That's pretty cool. Now you can actually have remote storage in less than 20 microseconds. What's going to be more cool, though, because our friend Oren at Mellanox was explaining to us day before yesterday now, wasn't it? That using the persistent memory on the card as the place to put the submission queues and completion queues and data in flight, then we can do a complete offload from the host machine. There'll be no CPU utilization on the remote machine and no memory utilization on the remote machine. And we believe at that point the storage will be below 10 microseconds for 4K random writes to remote persistence with actually no load on the host. This opens up all kinds of opportunities. We've always, I was an RDMA guy for years, and we've been trying to figure out how to, build scale-out environments where you can actually share, memory first with RDMA, now storage with NVMe over fabrics, and the capabilities there, especially once you get persistent memory on PCI, really open up, for you guys to do a lot more thinking. I'm a hardware guy. In fact, I'm a component-level hardware guy, not even a system-level hardware guy. And I know SNE is mostly about, delivering great storage software ecosystem. And I think that's hugely valuable. But we need you guys to think about what this kind of technology can be used for and how we should use it. I don't think the standards are done yet on how we talk to persistent memory on PCI. I think there's a lot of value in expanding that, and we just want to be a part of it. So, thank you.
All right, thanks, Terry. Our next speaker is Rick Kumar, Vice President of Product Development at New ISIS. Rick is the Vice President of Product Development and a provider of advanced data center products. Prior to New ISIS, Rick worked at Oracle for more than 15 years, serving in numerous project and engineering management, overseeing large global teams. Please welcome Rick.
Morning, everyone. I'll be talking about NVMe over Fabric and some of the things we need to consider as an industry as we implement Fabric in real-world environments. as you look at what's happening in the world, the latency continues to go down, but along with latency comes some of the management headaches that we as an industry have to consider. We've been working with our partners and with our customers to look at disaggregated storage and how disaggregated storage with NVMe-oF fabrics can be implemented. Obviously, latency has been a big driver of this force. With the efficiencies that it can deliver, we need to look at some of the management aspects of how we would implement it in large-scale deployment, particularly with cloud service providers that are managing hundreds and thousands of nodes at any given point. Disaggregation also brings efficiencies from both scale-up and scale-out perspective. So there are many, many benefits on how we would go about doing this. So management at scale, particularly for hyperscale customers, the feedback we've been getting and what the industry has been driving towards is how do we manage something out of band? Everything we talk about has been in-band management, but out-of-band management for security reasons have become quite relevant for our customer bases. So we're looking and working with our partners to deploy some of the RESTful-based APIs that would support open standards like Swordfish. And these things will enable customers to manage the enclosure health, the security, i.e. access to the storage itself, error monitoring, and firmware management, which we all have to deal with as time goes on. I'm going to be showing a couple of examples of some of the applications we're looking at deploying. The first one is a Cassandra implementation that we're working on with, again, customers in the industry. So Cassandra, multiple customers are using that out there. What we could look at is NVMe-oF fabric with multiple copies of the same data set across the network. With the host connected to it, some of the testing we have done has shown 50 microsecond latency on NVMe, standard NVMe, and certainly there are other technologies coming to market that will drive that number down. If you were to lose one of the storage nodes or one of the hosts, how do you manage failing over to another node or a host? And that's where the Fabric Manager comes in. We've been working on trying to implement something that does that centrally, such that you can manage the security, you can automate the storage features that you need at the data center level, and perform and do continuous monitoring of the health of the network, the errors, and anything else that the customer may need. And it allows us to fairly seamlessly fail over to another node with minimal disruption to the customer. This is an example of how one could go around implementing spectrum scale or GPFS in the industry. So this is, again, another node that's connected to a number of GPFS clients, servers, which are then connected to a number of clients. We've been able to demonstrate running RAID, so data protection across NVMe-oF fabric, and yet deliver with a full file system loaded on sub 90-second microsecond on the latency. Now, this did use Optane drive, so it was extremely efficient in that perspective. So these are just examples of how our node and the clients can grow in a data center very easily. And what we're advocating is driving a out-of-band management interface that complies with standards that are already out there. Thank you.
All right, thanks, Rick. And our last panelist is Dr. Andrei Vityaev, Chief Strategy Officer for Mobiveil. Andrei is the Chief Strategy Officer at Mobiveil, a silicon IP and platform developer for storage and IoT. He is responsible for new business development initiatives at Mobiveil. He has served as a founder and CEO of Proton Digital, an LSI fellow, and worked with numerous Silicon Valley companies. Please welcome Dr. Andrei Vityaev.
Hello. So I will talk about latency and throughput in SSD controllers for persistent memories. To introduce Mobiveil, we are a silicon IP and platform provider. We focus primarily on storage, but we also have products in networking and IoT. In storage in particular, we have this SSD controller platform that you see shown on the right, where we have various blocks that we license to customers, as well as in some cases, we also provide them a complete platform. So you see all the standard blocks within the controller, PCI Express, and NVMe controller at the center of it, flash reliability, /LDPC, flash sequencer for talking to flash, and so on. What is interesting is that we have to work with a wide range of customers. These customers have a wide range of requirements on the data rate and on the latencies in particular. So as a result of our business model, we are forced to stretch our blocks to a higher degree than perhaps what designers have to do at classical semiconductor IC suppliers for the controllers, because we face a wide range of situations. So as a result of that, it was necessary for us to create a high degree of scalability and configurability in this SSD controller platform. At the most basic level, the data path width of every blocks shown in this diagram is scalable and configurable. So as a result of this scalability, we are deploying this controller platform to persistent memories. So the platform originally was designed for classical flash memory, and is deployed in the persistent memory case. We did a press release yesterday announcing a partnership with Crossbar, where Crossbar and Mobiveil are applying this controller platform to develop a resistive RAM SSD and resistive RAM NVDIMM. So on this slide, courtesy of Crossbar, we're showing the performance specs of the resistive RAM SSD that is under development. Note that the performance numbers shown here are based on measurements of the existing components that will make up this SSD. For Crossbar, of course, resistive RAM has already been demonstrated at a previous conference. The latency of the memory itself in this sort of a large capacity configuration is 1 microsecond for the read and 2 microseconds for the program. There is no erase required, makes garbage collection a lot easier. For the controller, controller is a deployment of the Mobiveil platform controller that is configured for this specific application with its latency and throughput requirements, together with necessary customization and addition of some other components. So as a result, you get this NVMe module shown here on the right. Let's see if I can point this, not quite. So on the read side, the latency is 10 microseconds in the worst case. The random I/O performance is 6.4 million random I/Os at the 512-byte block page boundary. So the page size obviously doesn't need to be as big as it is in case of flash. When you're working with 4 kilobyte blocks, the numbers change, but the overall throughput is the same, 3.2 gigabyte per second. On the right side, the write performance is 10 microseconds without caching, and this is the worst case, 10 microseconds. The same random I/O performance, 6.4 million random I/O per second at 512-byte blocks. There is no erase prior to write required. As I mentioned, that eliminates garbage collection. Endurance is not unlimited. Actually, in this specific configuration, it's 100,000 write cycles. Crossbar itself has demonstrated at a previous conference 1 million cycles. They did a demo in the conference itself. But for the product itself, 100,000 cycles are specified. There are several technologies that allows Mobiveil to achieve this design specs. First is a scalable design. I mentioned that at the very basic level, the data path widths within the blocks are configurable, and there are other programmable and configurable parameters as well. The other one is that FTL is implemented in hardware. All the page-level operations are done entirely in hardware with the corresponding address lookup and everything else. In case of a flash version of the same platform, the block-level operations are handled by firmware, such as arrays or figuring out which blocks to allocate for writing into, but the page-level operations are done entirely in hardware. And this is the same implementation. Here, obviously, it's the same platform, and this is what allows us to achieve this performance specs. In general, we try to do control blocks by having programmable state machines and by having sequencers, instead of trying to insert various small microprocessor cores. So we found this design to be simply more scalable across different customer configurations. And we also found this design to be more reliable in terms of having lesser probability of a design error of some sort. So again, this shows an example of not sort of an ideal design when somebody gives you $300 million and tells you, go ahead and build the very best possible clean sheet design. This shows sort of a very practical solution, taking a platform that was designed originally for the flash implementation, but that has sufficient degree of scalability and flexibility that it can scale to this design and achieve this performance specs. So in case of the NVDIMM version of the design, this is much more parallel design. There are more channels here. There are 16 channels talking to, I cannot point this. There are 16 channels talking to resistive RAM chips, DDR3 64-bit wide interface. Latency drops for read case from 10 microsecond to 4 microsecond worst case. The random I/O performance is 24 million random IOs at 512-byte page boundary. Obviously, the numbers scale when you use 4 kilobyte blocks. Write latency also drops from 10 microsecond to 4 microsecond. This is without caching. And the same spec for the write cycles as well. So again, as I mentioned, all these numbers come from measurement of the existing blocks, measurements of the blocks that come from the Mobiveil controller platform, as well as measurement of the resistive RAM samples which are already available. Lastly, I want to touch on a completely different topic, sort of going back to the controller design in general. This is separate from crossbar implementation. Latency and error correction coding. ECC is a necessary element in every memory. It allows you to bring technology to market sooner. If your manufacturing process is not perfect and you're facing some errors, and when you're trying to read the data back, you can correct these errors with error correction coding. So as long as you have sufficiently low latency and high throughput and good implementation, it allows you to do more with the existing manufacturing technology. So the question is, what is the latency? There is a wide range of latencies which depend on the type of error correction code being used and the code word size and how many bits you're trying to correct. Because there are different types of ECC code, some of them based on algebraic decoding, some of them are based on probabilistic type decoding. So it's a pretty wide range of latencies and throughputs as well. When you're trying to correct only 1 or 2 bits per small code word, latency can be minimum. You can bring it down literally to just 1 or 2 clock cycles in the best case scenario. And then if you're trying to correct more bits, then you have to increase the latency. So we wanted to see what is the latency for the most powerful case. The most powerful ECC which is available, LDPC stands for low density parity check, can still have low latency. So as part of our controller platform, we have LDPC compiler that's been deployed in a few customers in production and all. So we run that software to generate RTL for a configuration that we think would have fairly low latency, and here are the numbers. So beginning of life, when this code has to correct few errors, not zero, but few errors, is 75 clock cycles. At the end of life, when you're getting close to full capability of what the code can do, you get into 155 clock cycles. The design has quite a bit of margin in it. So with the high density, with the high speed library, you can basically, this means 155 nanosecond latency at the end of life. But again, this design was really optimized for size of implementation. It wasn't actually optimized for latency. And the question is, can we do better? And the answer is yes, absolutely. We try to go through a process of figuring out what is the theoretically best case latency for LDPC, going through the algorithm, what it does, and looking at the sequence of calculations you have to do and what it would mean in digital implementation. And we get in numbers of 12 to 15 clock cycles at the end of life. So certainly something less than 20 nanosecond with the implementation that's geared towards lowest latency instead of smallest size. Okay. So in summary, this is what Mobiveil were able to do with this controller design that was scaled to a persistent memory application.
All right, so these guys are not just up here talking. They actually brought their stuff and are demoing it out here in the mezzanine area. So if you look for Everspin, they have an MRAM enabling low latency NVMe over fabric applications. NVMe over fabrics with all the standard drivers achieving surprising latency. And then we have from Mobiveil an FPGA-based SSD platform that incorporates PCI Express, NVMe Express, LDPC, ONFI, and DDR4 controllers. The platform includes FPGA board, FMC card, flash SODIMM, and hardware-based flash translation layer. An appliance from New ISIS is demonstrated that can be deployed today and supported disaggregated storage with best-in-class latency. Management software supports RESTful API that can be used for storage administration in a similar fashion to today's storage. And I believe there's also a Samsung demo out there as well, right, Bill? Yeah. So go check that out and ask questions. Speaking of questions, we'd like to hear from you. What do you think the impact of persistent memory will be on SSDs? What new standards might we need to do? And again, a reminder, we are streaming this live on the internet, so if you could, raise your hand, wait for Marty's microphone, and then ask your question of the panel. Just raise your hand, like this.
SW, you left.
Yeah, give him the mic anyway. All right, well, to get things started and so on, why don't we have a question for Terry? How would you use such a small storage capacity? You're talking a gigabyte drive, right?
Yeah, that certainly is a question we get often, right? I mean, the MRAM technology is extremely fast, and the endurance is amazing. We're talking billions of cycles, not hundreds of thousands of cycles with technology. But then what do you do with it? So the first and most prevalent use case is a write buffer to other devices. Okay, so you could take an all-flash array, you could put one of our devices in, it could be the write buffer for everything else, and use cheaper consumer-grade NAND for the storage and the other slots. There's also a bunch of interesting cases inside of an SSD itself, and it's still the same write buffering thing, but the big challenge with managing NAND today was already mentioned here, is garbage collection. And the fundamental issues around garbage collection are getting worse and worse every day because the NAND block size is growing. The common storage block size is 4K bytes. Many applications use 512 bytes. but the NAND block size is in megabytes and growing. So what happens is you end up with data stored in a NAND block that's from totally random threads, and now the garbage collection problem is amazingly a challenge, right?
And a bit of noisy neighbor as well.
Yeah. So if you can actually buffer enough data in flight to locate data in the NAND blocks that has some logical association with each other, now in some cases you've wiped out the garbage collection problem because it was all one file, you invalidated.
Sounds like streams.
Rates, right? But that takes an amount of buffering that's really not achievable in a U.2 form factor with supercaps and DRAM. So
Okay.
MRAM's a great use case for that.
Rick, Andrei, you want to address the question? No? Okay. Hey, we have a hand raised. Go ahead.
Thank you. I just have a follow-on question there. In terms of MRAM, what is limiting the geometry scaling? Is it scaling, and where do you see it go in terms of cost over time, compared with the DRAM as well as 3D XPoint? Thank you.
Yeah, so MRAM, the products we're shipping today are made from a standard CMOS foundry-based logic process from Global Foundries of 40 nanometers, okay? Our 1 gigabit chip, which would have been on display at Fire Memory Summit, was made a standard 28 nanometer technology. The scaling of the MRAM bit really comes down to the diameter of the magnetic tunnel junction, and we're scaling it down every 2 years. I joined Everspin 4 years ago, and not because of me, but during my time there, we've dropped the cost per bit 16x, and we don't see that changing for another, that trend line should stay for another 4, 5, 10 years, okay? There will be a day, we believe, where an MRAM bit is a smaller area than a DRAM bit, and then it really comes down to manufacturing scale.
Any other questions? All right. Rick, what are the benefits of disaggregation?
All right. So with direct attached storage, you're always forced to plan for worst case scenario. And with disaggregated storage, you can dynamically allocate storage to applications, to servers, and as the need changes, you can optimize your utilization of the assets that you have in your system, in your environment.
Anybody else want to address that? No?
I mean, disaggregation is fundamentally, data centers used to be built with, every machine being the same and there being a million machines there. And what data center managers found out was that they're wasting a lot of compute resources or a lot of storage resources or a lot of memory resources because every machine had to be configured to run the large job. With disaggregation of storage and other technologies, what we find is that data centers can be much more efficiently scaled, and it's great. We need more of it.
So we're moving away from direct attached storage, even though we were just moving towards direct attached storage.
It's a perpetual cycle, isn't it?
The use cases are so broad and the market's so big today, nothing is going to die in the near. Hey, look, tape drives are still heavily used, right?
Right.
So
That's really disaggregated. Any other questions? Come on, guys. This is interesting stuff. All right, back to Terry. How do you compare to Optane?
Another common question for us. The graph showed it. From a read characteristic perspective, all of the resistive memories, 3D crosspoint, phase change, conductive bridge, resistive RAM, they all have good read characteristics. No one's right on top of DRAM, and MRAM's in that category. We're not 100% of the DRAM kind of performance, but very close, within 2, 3, 4x in terms of the DRAM characteristics. That's not where the difference lies. I think 3D crosspoint is going to be an awesome technology if and when they can get it on the memory channel and pull a bunch of storage into an area where that you can access it very quickly for large-scale databases. What MRAM does, though, is it provides persistence for the writes that the other technologies can't do, right? So I don't consider the other storage class memories as competitors to MRAM. I think MRAM makes them all better because it can soak up the writes and then distribute it in the back-end storage in a way that the other technologies can deal with it. And, that there's not going to be one memory that's the whole world in the future.
Right.
Just like I mentioned tape drives, student tape drives, it's how you tier the storage hierarchy and how you use the different technologies to provide the benefits that our customers need.
Yeah, well, NAND SSDs started out very expensive per bit, and you would just put a little tiny drive in there to accelerate the rest of the
That's right.
stuff, right? So this is a new sort of acceleration kind of storage tier, right?
Yeah, and who knows where this storage tier ends up, and maybe it actually ends up on the CPU die because the technology is highly integratable
Right.
with standard logic technologies. So there will be a day where all memory except for the register files inside the CPU is persistent.
Right.
Maybe
So
maybe L1
We'll
is
swing
still
back
not
to DAS
persistent.
again. Other questions? All right, keep going. Rick, what management capabilities are needed to deploy at scale?
Right. So today, some of the standards that are available does management in band. As you grow the number of clients, as the number of users grow, would you want to trust your allocation of storage to the clients themselves? So what we've been discussing is creating an out-of-band management capability where your namespaces, your storage resources are allocated to specific clients and can be failed over or can be persistent across multiple environments. So you scale your disaggregated storage, but you also need to be able to manage who you give storage to and what storage is available.
What about Swordfish?
Obviously, want to integrate with that.
So he's going downstairs after this to participate in the Plug Fest.
So, Mark, there's a question that's coming in
Oh,
on the
yeah,
internet.
online, yes.
So,
Questions are
so and
available
I
from
think
the
it's a
internet.
question for Andrei, wanting to expand a little bit on, the impact or the meaning of security in a persistent memory system. Maybe expand on that topic a little bit.
Well, I think the issue is, you want to maintain low latency in case of security computations as well. Security computations naturally, involve obviously a fair amount of mathematics, but I don't think that the latency challenges in securities would be at the forefront of the latency challenges for the controller itself.
But doesn't security impact your latency? As you're
it does.
encrypting and decrypting, right? That isn't true.
It does, but also the question is how do you implement security? There's a very interesting sort of branch of mathematics involved in security with the number theory and all. And it's the same sort of subject matter as in the low density parity check codes that I mentioned. You can have a design optimized for silicon area, and you can have design optimized for latency. Mathematical formulas change. Mathematical formulas stay the same, but the implementation is different. So at this point, in terms of the challenges that we had to deal with, obviously trying to port FTL, most of FTL implementation into hardware, this required some work, especially because you're taking some algorithms and firmware that you can easily modify if you have an error into hardware where you have to guarantee reliability. So FTL challenges, required some amount of work. Some of the other blocks required amount of work. Security hasn't. We don't see it as a challenge in terms of latency. I'll put it this way.
Well, but what about when you're disaggregating and you now have your bits on the wire? They leave the box. Is that secure?
I think for that question, we probably have to bring some of the other people from Mobiveil to answer.
Anybody else want to address that? Rick?
We've seen different models being implemented for security. Some of our customers are actually going out and securing the data or encrypting the data even before it gets into the network. So what you end up receiving on the storage node ends up being encrypted to begin with. So from a latency point of view, you're not doing any compute, you're not doing any additional work at the storage level.
All right,
You're receiving the data already.
Just like the cloud, encrypt it before you get it there.
Right.
Okay. Yeah. You need a mic, wait.
I don't need a mic.
Yeah, the
Or do
people
not
on the
bother.
internet do. You're not that loud.
So talking about on the security side, I mean, we see some of the new processors offering inline encryption engines for the memory channels, right? So the AMD processor, and we're just putting the Linux drivers in for that now for key management and saying, I want this part of memory to be encrypted on the way to the DIMM or the NVDIMM or whatever. So are you guys able to leverage some of that where it can do the encryption of the data going to those kind of devices? Is that something that you guys have thought about at all, tying into that new hardware that's coming?
So it depends on the implementation and what the architecture is. From a disaggregated perspective, it doesn't really play into that aspect of things, but certainly if you had direct attached storage, you have to implement security at somewhere. And that could be done at CPU complex level or some other layer where the data is actually coming in secured. And if it's not secured, then you will consume compute cycles to make that happen.
I'd say certainly in our implementation of NV Nitro, if encryption on the fly was desired, the FPGA has plenty of space to add that in.
Another question? Okay, let's see if we have any. Back to Terry. Since NVDIMMs are mostly enabled now, why is persistent memory on PCIe interesting?
Well, I could give you my answer, but the gentleman at the back of the room will give you a much better one sometime today or tomorrow.
Next.
Yeah, in 8 minutes. So, the compute cycles are there for running applications, and what we need to do is deal with storage in the fabric.
Right.
Okay? And persistent memory in the fabric provides a buffer, a way to handle the queues, all kinds of things that you need to deal with at the memory level instead of the block level, and do it in a distributed way in the fabric, and keep that workload off the CPUs, the main CPUs, so that they can run the applications the customer desire. And like I said, Stephen knows far more about this than I do.
You can't hear you, Stephen.
Thursday? Is that Thursday? Okay.
Okay, no more questions from the audience. Rick, what performance can be expected with disaggregation?
So we've been doing different workloads. In certain cases where you're doing pure export of NVMe, we've seen latency as low as 40 to 50 microseconds. Certainly, again, with different technologies coming into the market, you can further reduce that. With file systems, again, we have been testing different file systems. GPFS, we were getting down to under 100 microseconds. Again, these are all ideal conditions where there is not a lot of network congestion, so network plays into this, and that's something, again, we're working with customers to figure out how to architect that in their environment. But from a pure execution perspective, 100 gig network going to 100 gig network, we're seeing very, very competitive latency and disaggregated storage.
But what are you comparing that? Are you comparing that to DAS? Because
No,
as soon as you remote it, you're going to suffer performance, right?
You will.
Yeah.
Yes.
So, okay. And if there's no more questions from the audience, huh? Okay, we want to thank our panel.